Okay, so hello everyone and welcome to the second YES workshop. Today, Kien and Miguel will present about remote sensing and we hope you're going to enjoy the session. In case you want to contribute to the YES task force or if you have any requests about specific workshops, please feel free to reach out to yestrainings@gmail.com. So to you, Ray.
Okay, cool. So let me share my screen. You can see it, right?
Yeah.
Okay. So, okay. Hello, welcome everyone to Introduction of Remote Sensing Application Service. My name is Kien and I'm a graduate student in the National Central University where I work in the Center of Space Science and Remote Sensing Research. And joined with me today is Dr. Miguel. He's a postdoctoral research fellow in the Eastern University of Life Science and the University of Eastern Finland. So this session is going to be divided into two parts, with the first part introduce the fundamental and basic characteristic of remote sensing data. And in the second part, Dr. Miguel will talk about the challenges of assessing and mapping a surface using remote sensing. So without any further ado, let's get started. So we want to start with a basic question about what is remote sensing. As we know, many of you have heard about this term or know about remote sensing data, but actually never used the remote sensing data in your work. So for me and for some of my professors, simply put, remote sensing is just a science of extracting information from reflected light. So for example, our human eye is a complete remote sensing system, allowing us to decipher the reflected energy coming from objects and turn that energy into information. So for example, we can see the tree with the green color simply because the leaf absorb most of the green and blue colors and reflect most of the green color. And just by looking at the tree, we can partially know about the plant health status, but our eye system are limited in a visible region. So it's ranging from 0.4 to 0.7 micrometer. So you could also know as blue, green, and red colors. So we designed the satellite sensor that could detect and record a wide range of electromagnetic energies. So for example, ultraviolet, infrared, microwave as well. And this provide abundant resources and information for our research and work. So depends on how the sensor detect and then record the energy. We divided them into passive and active sensors. With the passive sensor is the most well-known and a more common one. It's utilize the reflected sunlight. So the sun illuminates the surface, and part of the energy will be absorbed, transmitted, and part that will be reflected back into the skies. So the sensor will record that energies. It also can measure the thermal radiation. So it enables you to actually compute, for example, the urban heat island effect. It's easier for interpretation, but it also sends it to the weather condition. For example, if there's a cloud present in your image, you won't be able to see beneath that. So to compensate that, we designed the active sensor, use the our energy. So because it uses our energy in the much lower frequency, it's able to penetrate through the cloud, and it is independent for daylight and weather. So of course, you might hear about active sensors techniques such as SAR, like a synthetic aperture radar, or LiDAR, light detection and ranking. So these technologies are a bit complicated to work with because it's not similar with the way we use our eye. But with the advancement of technologies, we are now seeing the chance of using the data set more and more in environmental monitoring and natural resources assessment as well. So we can use that for retrieving vegetation, soil, and snow characteristics. And satellite orbits is the third part that really important when we're choosing the satellite data for your research. There's many ways to put the satellite into the orbit. I want to mention two most well-known, that is geostationary satellites and polar and near polar satellites. So geostationary satellite orbit in a very far from the Earth with a very wide field of view that can scan the entire part of the Earth in one single image, and it can provide a lot of image in a very short time. And it's rotating around the Earth in the same speed of the Earth rotating around itself. So it actually always stay in one fixed location above the Earth. That is really convenient, convenient for transmitting signal for telecommunications and weather forecast monitoring. But of course, because it stays really far from the Earth, the image, the spatial resolution image from geostationary is very coarse. So to compensate that, we also develop polar and near polar satellite. They travel in a much lower orbit, and from the north to the south, parting, or the south to the north, depends on the design. And it passing the equator and provide a part or global coverage in hours or day. So many polar satellite are also sun synchronous satellite, which means they pass the same area pass the same area at the same time for every cycle. So for example, like today, the Landsat image, Landsat satellite passed to my home at 2 p.m. 16 days later, it will come back here around 2 p.m. and take another data set as well. So this opened the opportunity for you guys to compare the changes of one area in different years. So here's an example of Himawari images. It's a satellite developed by Japan. It's a geostationary satellite. It provides 1 minute for every 10 of one image for every 10 minutes. Sorry. But of course, it's very far from the Earth. It covers part of ASEAN, Australia, and Japan. And here's another illustration of satellite Landsat 8 and 9 with a much lower orbiting at 400, around 400 miles above the Earth and with a very narrow field of view. So we just briefly mentioned two sensor resolution, that spatial and temporal resolution. And there's 4 of them, that spatial, spectral, radiometric, and temporal resolution. It's really important characteristic when you guys want to choose the appropriate or suitable data set for your study. So we go deeply into each of these sections. First is spatial resolution, denote what you can see in the image. For example, here we have the planetscope 3 meter. And if you zoom in that, you know the pixel, the image actually made up by a matrix of pixels. And the size of each pixel is actually referred to the distance on the ground. So for example, the Landsat, the planetscope in here, we have the spatial resolution at 3 by 3. It means 1 pixel covered the area of 3 by 3 meters on the ground. So anything that's smaller than the pixel, won't be able to detect on the image. So what does that mean? There's more example for you guys. We have modis 500 meter in here. So each pixel cover area of 500 by 500 meter. So a lot of things you can't detect many things in here. It's just a size of pixel. It's more suitable for a study with a large area, for example, like a country and a continent. So if we have higher resolution image, for example, Landsat 8, it's 30 and 30 meter, you will briefly know that image is actually about the coastline, but you won't be able to see anything that's smaller than 30 by 30 meter. For example, you won't know if there's man-made infrastructures or other material on there. So Sentinel-2 provide a better spatial resolution image at 10 meter. And you now can see there's housings and vegetation feature on the ground. Of course, planetscope have 3 meter, it give you a better interpretation, more accurate interpretation of what is actually in the ground. But of course, high spatial resolution is better for interpretation, but not always better for your study. It really depends on your study design. Sometimes if your study covers a very large area, it's better to use a bit coarse image because there's a limitation in the trade-off between different resolutions and of course your hardware processing ability as well. So the second resolution is spectral resolution. So when the satellite records the energy reflected from electromagnetic spectrum, it records them simultaneously, and not only visible, but also in other domains like near infrared, short-wave infrared, and thermal infrared. So spectral resolution refers to abilities of the sensor to record the energy in different bands and how narrow the bands are. For example, multispectral satellite usually have 4 to 10 to 12 bands, and they measure the specific section on electromagnetic spectrum, like in visible, in near infrared, and so on and so forth. And hyperspectral satellite, they can produce hundreds of bands, and it continuously measure across the entire electromagnetic spectrum. So put in a simple way, multispectral satellite image from multispectral satellite can help you guys distinguish forest from urban and water area. Then hyperspectral satellite can give you more detail to discriminate the species of the tree inside that forest. And here is the enlarged image from red Landsat 4 bands. And you can see the vegetation absorb. For example, you can see the vegetation absorb a lot of red color. So it's and not reflect a lot of red color light. So that area will be darker. Meanwhile, the near infrared will reflect a lot of light, near infrared, right? And based on, so the spectral response is just a biophysical and biochemical characteristic of the land features. And we're trying to use the information to extract more information for our model, for our output and assessment. So the third one is radiometric resolution. That actually the ability of the sensor to differentiate the level of reflected light, and you can call that as bit depth as well. So what is actually the level of reflected light? Here we have the image of 2-bit image, 1 bit with only 2 possible level. So every pixel in here is either black or white colors, and you won't be able to differentiate the object on the ground. And if we have a better radiometric resolution, like here we have 2-bit image, we have 4 different grayscale. So you will briefly see, okay, there's a look like an urban area with housing block. So moving with higher spectral resolution, you have better range of value for pixel aside the brightness for the pixel. So you can discriminate the object easier. So of course, our eyes are limited in the fixed amount of grayscale we can see, but we can use the computer ability to computing them. So for example, here's some example of a sensor, image from a sensor with different radiometric resolution. Landsat 8 to Landsat 4 to 7 can provide 8-bit images, and Landsat 8 can provide 12 bits, and after processing, it can increase to 16-bit. MODI and Sentinel also provide 12-bit images, and the newly launched Landsat 9 provide 14-bit images. So the last one is temporal resolution. It's actually referred to the amount of time the satellite takes to revisit the same location and take the data from that location again. So just now we mentioned geostationary usually offer higher temporal resolution. Like Himawari it can capture 1 image for every 10 minutes. Meanwhile, those are Landsat or Sentinel, they have higher spatial resolution. So they usually have their trade-off between spatial resolution and low temporal resolution. So they have much higher temporal resolution. So one way to increase the temporal resolution of these satellites that are putting more satellite with the same characteristic into the constellation, and they will have overlap. So for example, with the new Landsat 9, NASA just launched, instead of 16-day waiting, now we only wait for 8 days every time with a new data set. And it's reduced from 10 days for Sentinel to 5 days. So as we acquire the image from the satellites, we'll look at the visual interpretation of the image. So here's the image of a red band. When you first take it, you will first look, I believe you should first look at the shape and the size of the object on the ground. That gives you a big information about what is that on the ground and where is that from, what is the surrounding environment is. And we will look at the brightness from the pixel. So red band, as we talked about just now, red band vegetation usually absorb a lot of red light color. So the dark pixel likely to be vegetation, and those brighter maybe the urban area. You can look at the pictures and the patterns, and you can recognize this actually look like a road on the map, right? And you extract the feature. So because the satellite can record a lot of different image in different bands. So instead of traditional natural color, like the way our eyes look, we assign the red band to the red color, the green band value to the green color, and blue band value to the blue color. We will have the natural color exactly similar with what our eyes see in here. But we also have data from other domains as well, like near infrared and thermal infrared. So if we assign that pixel value in different color, we will have something called full color infrared. So in here, it's very well-known full color infrared images. Instead of putting red color in red pixels in the red color, we put the near infrared bands in the red color, red in the green, and green in the blue. So all the vegetation area will now reflect a lot of near infrared and will be brightly red in here. And this is actually really helpful. For example, if you just look at the natural color image in here, you won't be able to discriminate what it actually, I'm not sure, let me turn this on. So here, let's look at this small spot in here, okay? It's look like a green color, so it's look like a vegetation area, right? But when we change the composition, this actually reveals that it's a lake or the small receiver instead of vegetation cover. So by stacking the image, by stacking the different band in different color domain, we will have more information depends on the spectral response of the lens feature. So there's a lot of different combination. You can check that on the internet, and each sensor, because the sensor design differently, they provide different bands. So there's specific combination for each sensor. But you can find that easily on the internet. And for example, here's an agricultural composition with the software infrared, near infrared, and blue from Sentinel-2. It's really helpful. It's really good to detect the healthy vegetation with the bright red color, and those area with the darker green color mean they are under the water strata. So just now is detect the land features visually. How about if we extract the information for specific phenomena that you are interested in using the computer process ability? So it's called spectral indices and environmental variables. So to extract these phenomena that you're interested in, first you need to choose the bands or the wavelength that are sensitive to the properties of your interest, and develop the mathematical formula to combine them. So what is combine the band is actually here, for example, we have the image near infrared and red infrared, near infrared and red bands, and each pixel in there will have the L value reflecting the brightness of that pixel. And combining them mean apply the formula to each pixel in the same location. Here is like just briefly subtract the near infrared value by the red value, and we will have the difference in the brightest pixel value. Of course, the formula to combine them are more complicated than just that. There's a lot of spectral indices have been developed by scientists, and one of the most, I think is one of the earliest developed is, and most well-known in normalized different vegetation index, where it's based on the idea based on the normalized difference between near infrared band and a red band. So you can see the grass in here absorb a lot of red color, but then reflect a lot of near infrared light. But in the same time, it's also the grass, when it under the water stress, the curve is much flatter, and so the value in here, the value of a raw glass will always higher than the dry glass. Based on this, you can calculate the NDVI value of that pixel, and each pixel of that image, and each pixel will have their own NDVI value. And from this, you can use that as input for your environmental model or custom survey model. And you can also extract the pixel that has a high value of NDVI and reclassify them into, for example, healthy, unhealthy, and moderate vegetation. Of course, this is just demonstrate. Normally, we don't use a fixed threshold for detecting or classifying something based on only one spectral indices. And during the time, there's a lot of spectral indices and environment variables has been developed. And here's some of the most commonly seen in ecosystem survey research. Normalize different build-up, vegetation, and water index, leaf area index, normalize burn ratio, and land surface temperatures, land use, land cover. So if you're familiar with some ecosystem survey assessment software like Invest, it's always asks you to have some spectral indices involved in there. And I think I always see the land use, land cover, and at least early land use, land cover, and depends on what you want to classify, assessment, or mapping. You need to use more spectral indices. So there is some software and programming language can handle remote sensing data. And I will briefly introduce some of them. The first is commercial software that we talk about: NV, NDAS, Ecognition, and ArcGIS from Edris. And those commercial software, they are developed for you by the company. So most of the process has been, taken care of by them. And you might just need to understand and put a very minimal input that is allow you to manipulate the remote sensing data. But of course, there's a disadvantage of this. You need to pay a lot of money for use the commercial software. So instead of commercial software, you can use open source software such as Sentinel and Ophiel Notebook. QGIS and GAS also very famous and has been developed by a lot of different science communities and support by different universities around the world. And the third one is programming language that allow you to have highest degree of manipulating remote sensing data. And some of the most commonly is Python, R, MATLAB, and JavaScript. So here is some additional learning resources that I think is really helpful for different people for the beginning or introductory courses. I highly recommend the Spatial Analysis and Satellite Imagery in GIS that taught by Don Boyce in Coursera. I believe you can access this one for free, at least in the auditing mode. And for more intermediate user, you have Spatial Data Science and Application course also in Coursera taught by Jun Hyo. And there are two books I highly recommend if you can borrow that from your libraries or purchase that by yourself. The first one is Fundamental of Remote Satellite Remote Sensing, an environmental approach written by Emil Chubetko. He's a lead scientist in the field, and you might bump into his name here and there. And this is suitable for beginner level, and I think it's quite easy to read, even if you don't have much experience working with remote sensing data. And the second one is Remote Sensing Handbook, published by CRC Press. It's actually include 3 different volumes, and it's a bit harder to understand and to follow. So I think that is the end of my part. Thank you for your listening. And let me stop sharing my screen now. Okay. And I think we have a lot of time. I think I take like 30 minutes. So now I would like to, if you guys have any question, please put it in the chat and we will come back with your question now. I think we have like 5 to 10 minutes for answering a question before moving to Miguel. Oh, so Helena, she asked, is that a good idea to use RStudio and QGIS for land use, land cover? Yes, it's really good ideas for land use, land cover in QGIS, I believe. And I believe most of the commercials and open source software can handle land use, land cover. And of course, there are a lot of different techniques to classify land use, land cover. And I think QGIS and RStudio can handle it very well. And Miguel, if you have any other inputs, kindly help me with this as well.
Yeah, I think for land use, land cover, if you want to move away from the commercial softwares, Actually, QGIS has this absolutely amazing plugin, which is the Orfeo toolbox, which you already mentioned in one of your slides. And so using the Orfeo toolbox, you have this like basically set of tools that you can use to classify satellite data and create your land use land cover maps. And it doesn't require any programming. And then if you want to move a little bit into the programming side, there's plenty of R packages that also don't need too complex programming, you know. So there's definitely, yes, good idea. And I would absolutely encourage everyone to use techniques to calculate land use land cover. One of the most used is, I would say, random forest for classification or support vector machines. Kien, I don't know, I think what's your experience?
Yeah, I use, like, there's a lot of different one. We have machine learning and AI. It's like now really have attained a lot of interest. And traditionally, we have supervised classification and unsupervised classification. We have persistent trees and random forests as well. Mm-hmm. We have classification based on spectral indices, as we did just now in PCA. So there's a lot of way to classify land cover. But I think now machine learning and AI is one of the best. I think attract a lot of interest around the scientific community.
Yes, and I think it all depends what's your starting point. If you have some training data sets, then you would go into something like a supervised classification, like a random forest, support vector machines, or something of that kind. And if you wouldn't have any prior data, you would just have your satellite images and your spectral indexes, then you would use the unsupervised techniques, and then you would be using the k-means maybe, or an isoclast. But all these you can definitely use in QGIS.
Sure. So Lucia, she just asked if what a good website to download satellite images. So I would recommend, first, I would recommend Earth Explorer, where you can find Landsat image, Sentinel, and MODIS image as well. And of course, you can also access Sentinel in the Sentinel hub. And if you are a scientist and have a education email, you can download high resolution image from Planet. There's a company where they allow scientists to download 3 meters spatial resolution image. I believe there's an upper limit, but maybe this is very high upper limit for scientists. Well, okay, sure, let me write it there, Planet. So do you guys have any others question regard to the fundamental of remote sensing? And all right, Lucia, if you want, you can also try to download it from the Google Earth image, Google Earth engine, if you know how, if you can use coding, because it's allows you to download a lot of data in one batch, because Earth Explorers and Planet, they are basically a portal where you can select a single data set. And if you use Google Earth engine, it will allow you to download a lot of different data sets in one time as well. Yes, exactly, yeah. So if you guys don't have any other questions, I will pass this one to Miguel. So again, Miguel is one of the guest speakers today. He's a researcher in the Estonian University of Life Science and the University of Eastern Finland. His research interests include remote sensing data, remote sensing, ecosystem survey assessment, landscape ecology, and he will share his insight and experience about mapping and assessing ecosystem survey using remote sensing data. So thank you, Miguel.
Yeah, thanks a lot, Kien, for the invitation, and thanks a lot actually for your presentation, because that was super complete and thorough, and I think it very much sets the ground for what's coming now. So let me start sharing my screen. Now I hope you can see the presentation. So yeah, what I want to talk to you about today is it somehow stems from my experience in the last years working with remote sensing and working with ecosystem services. And it's basically what sort of challenges we're going to find as a mapping community when we attempt to map ecosystem services using remote sensing. So I think undoubtedly the biggest challenge that we are facing as a mapping community is the idea of capturing and mapping change in a consistent manner. During the last years, we have developed plenty of models for ecosystem services supply, and you mentioned, for instance, Invest, and we have developed these complex models and even simulations, but still it seems that mapping change in a consistent manner it remains a bit of a challenge. And perhaps the first question is, why do we need to address change in the context of ecosystem services? And this is very clear, that the scale of impacts and change on ecosystems is increasingly transnational or global. So we see, if you think, for example, about forest loss, is absolutely a global phenomenon. If you think about permafrost thawing, is a clearly regional, transnational, circumpolar phenomenon. So then that's about the impacts, about the scale of drivers of change. This is also increasingly transnational or global. If you think, for instance, about bilateral trade agreements between nations and the impact they have across countries, or if you think, for example, about the Green Deal or very clearly the Common Agricultural Policy in Europe, these are the drivers that create change throughout countries, throughout regions. So, you know, if we want to produce results that are relevant in the policy sphere, then we really must be able to connect these underlying drivers of change with impacts on ecosystem functions, with changes in the supply of ecosystem services across temporal scale. So we need very consistent assessment. We need to provide estimations of change at these scales, and this needs to be done with extremely consistent methodology and through very thorough validation schemes. And here's where remote sensing comes in as an absolutely amazing tool for many reasons. First of all, we can use remote sensing as a way of mapping and assessing proxies for ecosystem conditions. So we can map disturbances, like I said, forest loss, landscape fragmentation, shrub encroachment or land abandonment, and soil moisture, land surface temperature. We can use remote sensing as well to map proxies for ecosystem processes and functions. So changes in primary production, variations in flood control, coastal protection, and very importantly as well, we can use remote sensing as a proxy for biodiversity. And we know that biodiversity underpins, and in some cases is directly related with many ecosystem services. And on top of all this, the great thing about remote sensing, specifically satellite remote sensing, is that we have a high and very consistent revisited frequency. So we can actually detect these temporal trends, these changes in condition, these changes in ecosystem service supply. And we have relatively high ground sampling distances. So that was the pixel size that Kien was talking about. So we can actually capture those fine, very fine landscape patterns. We can describe pretty accurately those service providing areas. I'm not going to go in details through this because it was very well covered in the previous presentation, but we have a huge choice these days of platforms, a huge choice of sensors. We've got the Sentinel missions, including optical, SAR, thermal sensors. We've got MODIS, which has a huge spectral resolution. We've got 33 spectral bands, 36 spectral bands. And then we have the Landsats that go back about 30 years. So with the Landsats, we can really address these like really long-term timescales. And then we have some new satellites. For instance, we have these LiDAR satellites, the JEDI mission or the ISAT. So a huge choice of tools to address mapping of ecosystem services. And truly a very unprecedented volume of data, which is actually freely available in most cases, right? And if we look a bit more in detail about Copernicus and the European Space Agency program and the Sentinels, so we have this high revisit time. So every 5 days, we have one Landsat coming over the same point on Earth. And we have a very detailed spatial resolution that goes from 10 to 60 meters, depending on the band, and 13 bands. But not only we have this very interesting reflectance data from Sentinel, but actually what the Copernicus platform has done is that they have processed some of these data into ready-made products. And for instance, what you see here is one of the products that you can download from the Copernicus website. This is the tree cover density. Each of the pixels in the image represents the percentage cover of trees in Tallinn, in this case, capital of Estonia. And why is this absolutely fantastic is because this is truly a tool that streamlines remote sensing into ecosystem services assessment. This means that I don't any longer need to be a remote sensing specialist. If I am a spatial planner, for example, or a policymaker here in Estonia, I have these ready-made products that already tell me a very interesting story. And this, for instance, this tree cover density has a direct input into city spatial planning. So great amount of data sets out there, from the raw spectral images to some data sets that have been already processed. And this is a depiction of all the satellites that we have currently orbiting the Earth, actually -1 that Russia blew a few days ago into pieces. But anyways, all the satellites orbiting the Earth. And what I want to represent with this is that the data needs is no longer a problem. The availability of data is there. We have these huge long-term time series. We have these massive spectral resolutions. The problem now is how to make sense of this data, how to treat this data in a consistent manner, and how to ensure that we are targeting the right policy questions and that we are using this data the best way we can to truly ensure the sustainable supply of ecosystem services. So we are talking about ecosystem services maps, but how do we move, from remotely sensed data, from all those beautiful satellite images? How do we move to maps of supply and change, especially change? Because satellite images on themselves are just very beautiful depictions of change on Earth. I mean, of course we see change, but what is exactly changing? And let me show you a very good example of this. This is a map of greening and browning trends in the circumpolar Arctic. This has been done, amazing work, by the way, by Logan Berner in 2020. This was done using NDVI derived from MODIS and calculated in the manner of a time series. So this is great. We do see trends. We do see areas of the Arctic that are massively greening, and we do see areas of the Arctic that are browning as well. So, and we see the location of these trends. But what I don't know is which habitats exactly are being affected. So how is this greening process happening? And most importantly, why is this greening process happening, this greening and browning? And we know this has a massive impact on the ecosystem services supply, especially if we think about carbon storage. But just by looking at these trends, I don't know much. So here's the first and foremost, most important linkage to couple remotely sensed data with supply and change maps. And this is the need of field survey and ground truthing data. It is just through field survey data that we can actually make some sense of what we see from space. And it is through field survey data that we can disentangle really this spectral signal. So Lisa Norton in 2018 calls for the adoption of very consistent and effective sampling approaches. And she mentions that these sampling approaches should be based upon underlying stratifications of the regions that we are studying. So that means that when we are going to collect field training data sets, we must ensure that we are capturing as much as possible the environmental variability of the region. Number two, it's very important that we find concurrency between field and remote sensing surveys. That means that the capturing of the remote sensing images and the field data should happen at the same time. It doesn't make sense if I go on the field on 2016, measure topsoil moisture, and then use a 2020 Landsat land surface temperature, because they simply don't match. And then we need to define commonalities across field and remote sensing data. So that means that we need to thoroughly think through what kind of remote sensing data actually fits my field survey data. And so what variables should we measure from space? This is a very important question. If we attempt to map change in ecosystem services, we must look for those variables that allow the quantification of rate and direction of change of ecosystem services supply. You know, if I use, for instance, simply albedo, which is just reflectance, I am not getting much of a story in connection to ecosystem services. If I use, instead of albedo, land surface temperature, which is actually directly influenced by albedo, then I can start to make some conclusions about certain ecosystem services supply. And if I connect the land surface temperature with topsoil moisture, then I can get into the modeling part of it. And this leads to the second point, which is that we should measure or attempt to measure those variables that can be monitored based on the integration of satellite remote sensing, in situ data, and models. And why satellite remote sensing is because it's the only source of imagery that will give me fixed temporal, spectral, and spatial scales. A very good article, a bit in line with the question of what we should measure from space, is this one by Andrew Skidmore. And Skidmore is one of those leading scientist in the remote sensing, one of those big papas of the remote sensing community. So I recommend you do go through his amazing works. And priority list of biodiversity metrics to observe from space. This paper goes in line with the work that the GeoBond community has been doing for the past few years. And the GeoBond community came with a list of what they call essential biodiversity variables measurable by remote sensing, or EBVs. What the GeoBond has attempted with this list of essential biodiversity variables is to define a common framework for monitoring biodiversity, filling data gaps in the spatial and temporal coverage of in situ biodiversity observations. You know, we have these many monitoring networks. For example, we have the ELTER network, and these are made of, let's say, it's a network of points across the world, right? So what the GeoBond attempts with this is to fill those gaps between those monitoring points by using remote sensing. So the idea is to provide a set of measures that capture biodiversity change. And biodiversity change here is understood as change in ecosystem structure and function, changes in community composition, species traits, and species populations. And of course, these EBVs are scalable, and they can be monitored using global remote sensing data with those predefined temporal lags, which is the temporal coverage. So basically, what the GeoBond says and proposes here is to monitor change in a continuous, harmonized, and consistent manner. And although this does not address ecosystem services directly, it's a very good starting point, because these essential biodiversity variables, this framework, allows for comparability and consistency across regions, which is what we are talking here. When we are mapping change, we need really this comparability across regions, across biomes, you know, across countries. So, and how these essential biodiversity variables were selected was on the basis of those 3 points there. So first of all, relevance, and relevance understood as relevance for ongoing policy processes. So again, going back to the point of trying to answer the relevant questions with our remote sensing data. And then feasibility of assessment in terms of temporal resolution, spectral resolution, and spatial resolution, and accuracy of the potential sensed, let's say, remotely sensed variables. So I do recommend that you have a look at that paper by Andrew Skidmore, and it's very inspiring. And like I said, even if it's not directly connected with ecosystem services, I think it sparks a lot of useful ideas for our community as well. And in connection to what I just said, in connection with the fact that these EVVs do not directly address ecosystem services, the main questions that we should be asking ourselves every time we attempt to map is, what are we mapping? Are we mapping ecosystem processes? Are we mapping ecosystem functions? Or are we mapping ecosystem services? And Nathalie Petrarelli, another fantastic author here, she laid it very clear. She says that there's a need to define typologies of definitions in order to have a very clear understanding of what are we looking at. So, and we have seen in the last few years through the scientific literature that ecosystem function has often been used as a synonym of ecosystem service, and this is a bit of a dangerous trend. So if we want to have a very clear communication, because remember that maps are also communication tools. So if we want to have a very clear communication and very solid assessment and monitoring schemes, we really need to define a typology of definitions. And Nathalie Petrarelli puts it very clear in connection with remote sensing. She defines these three components of the system, starting from ecosystem processes, understood as the transfers of energy, material, or organisms among pools in an ecosystem, and then moving from processes to ecosystem functions, understood as those attributes related to the performance of an ecosystem that are the direct consequence of one or more ecosystem processes. So we're talking about water supply, nutrient regulation, and then finally, ecosystem services. As you all know, the benefits that we gain directly or indirectly from this ecosystem function. So the point here is, when we are using remote sensing, especially when we are using remote sensing for mapping change and for mapping ecosystem services, we really need to think through what component of this system on the left of the slide, which component of the system are we directly mapping, and which component of the system are we actually deriving from that map. And yeah, then a new challenge arises, which is the challenge of indicators. So mapping ecosystem functions involves necessarily a choice of indicators, and also when we are using remote sensing. And the same goes for mapping ecosystem services. So I do recommend that you go to this paper, and there's a fantastic table there where Petrarelli connects the functions with the remote sensing proxies and the remote sensing data products that we can use as a proxy to measure each function. And I think it's best to illustrate this point of processes, functions, and services mapping with an example. And I'm bringing you here an example of work we did in Estonia a few years ago already. Just to put you into context, Estonia, although it's a very, very tiny country, it has around 110,000 hectares of these very rich, very biodiverse, so-called semi-natural grasslands. These are grasslands that have been managed for centuries, and what we find is massive habitat quality and biodiversity. The problem is that currently we see a process of marginalization of this agricultural land. This means a process of abandonment. So we face the challenge of how to preserve these grasslands. And one new management idea, which came out a few years ago, was to use the grass to enforce the cutting of these grasslands, which is the management, and use the grass as a source of district heating in those areas of Estonia that are a bit more energy poor, let's say. And this is pointing directly at one ecosystem service, which is classified by the sizes, which is the use of wild plants as a source of energy, in this case, the use of grass for district heating. So this basically means burning dry hay bales, right? So before getting into any further developments, we thought that we needed to map the amount of the resource that we are talking about at the national scale. So our aim was to estimate the amount of grass biomass available at these semi-natural meadows in Estonia, and we did so by using Sentinel-2 images, and we, like Kien said before, we converted those Sentinel-2 bands into vegetation indexes, and then we, with the help of colleagues from different universities, we collected 500 field samples across different habitats. And here's that point of field survey data, the need of field data to train your models. Anyhow, so 500 field samples, Sentinel-2 images, and we developed this very interesting model of standing above ground biomass. And that's what you see, for instance, on the image on the right is one of the results of the model. This is an area in West Estonia covered by coastal meadows, and you can see how much biomass is standing there on an average season, right? And if you see the image on the top left, that's just a different type of grassland. That's a flooded meadow, but again, the same story. How much biomass is standing in that flooded meadow? Now, have I created an ecosystem service map? No, I haven't created an ecosystem service map. What I have done is I have mapped an ecosystem function, which is primary productivity, through a proxy, which is above ground biomass, which is a process. But I haven't yet mapped my my ecosystem service of interest. So in this case, I need to complete my assessment with ancillary data. And in this particular case, that data came from taking some of the grass samples into the lab and burning them and assessing the energy yield or the calorific power of different grass types. And then with that data, then I can plug that into my remote sensing assessment, and then I get the potential energy yield, which is the map that you see on the lower left corner. And that is already an ecosystem services map. So it's very important to consider at all times, are we looking at functions, are we looking at processes, or are we looking at services really? And then when we talk about mapping change, we need to talk also about mapping seasonality, about those very subtle variations that happen within the year in ecosystems, otherwise known as phenology or phenological changes. These are, in some cases, very, very subtle variations, but they can truly reveal some interesting stories. And then to illustrate this, I come with another example, I think this one is very interesting. This is a work we recently finished in the Gulf of Mexico, in Isla del Carmen, which is located very close to the Yucatan Peninsula. And what's the situation in Isla del Carmen? Imagine that the place is almost covered fully by mangrove forests, as you can see down there in the lower right image. So I think 80% of Isla del Carmen is covered by mangroves. Now, you may think of this place as some sort of tropical paradise. The truth is that Isla del Carmen has been affected by decades of pollution from urban sources, from agricultural sources, a lot from oil extraction. We have these oil fields very close in the Gulf of Mexico. But at the same time, these mangroves are key for the local communities. So they support, and most of you know, you work probably with similar ecosystems, they support fisheries, they provide protection from flooding, incredible carbon storage. So you can see the key role of mangroves as an ecosystem services supply for these communities. So our idea was that, okay, we have this, and this has been recorded for the last decades, we have this massive trace element pollution in the island. So surely this trace element pollution is affecting mangroves in one way or the other. And we thought we can approach this from the remote sensing perspective. So what we did is one colleague of us went to the place and collected several sediment samples and analyzed the content of these trace elements, the content of copper, the content of lead, etc. So again, field data. Do not forget about the field data. And then we said, okay, if we are able to combine like one vegetation index from Sentinel data, and in this case it's a different variation of NDVI, it's NDVI-RE, we sure will see some changes across the pollution gradient, right? And because we are expecting to see a change in mangrove vigor, in how lush the mangrove is, we expect to see a change. Perhaps we will see something related to the decay of leaves and etc. And we happily addressed this assessment, and what we found is that there were absolutely no differences in our vegetation index when we compared the values of this NDVI across the different pollution sites. So, you know, it's very tempting to jump into conclusions and say, okay, maybe these trace elements do not have so much of an effect on the mangroves at Isla del Carmen. But here's when we need to disaggregate our readings and go again into this mapping of change. And the problem here is that we were using just one snapshot. We were using the values of NDVI for a very specific time of the season when the mangroves are at its most lush stage. Now, what happens if I use the Sentinel series and I disaggregate and I create these phenology profiles? So I look at the timing of phenology events like start of the green up, start of the season, or length of the season. Then is when I see that there was a clear effect of those trace elements. In this case, you see the effect of lead and barium in the timing of the start of the season. So I have disaggregated my remote sensing data into a time series. And what I see is that trace elements, what they are doing is they are causing a delay in the start of the season of the mangroves, and they are causing also a shrinking of the length of season. And this, of course, has potentially a very harmful effect on the capacity of mangroves to deliver services, because they are more prone to impacts. So this is an example of how sometimes just one snapshot, one point in time is not enough. We need to disaggregate our data. And then you see these interesting trends. And then moving a bit beyond the raw spectral signatures and this raw satellite data, there's a lot, like I already said before, a lot of global satellite-derived data products that are there ready for you to use. Example is the tree cover density, but also Copernicus has produced, for example, maps of imperviousness, so the degree of soil sealing in cities derived from sentinels and ready to use. What you see in this image is one of the, I think, most well-known ready-made satellite products, which is the Hansen forest loss or forest change map. Extremely interesting to see and detect trends now. So these tools are fantastic. You know, we know that they have been, these maps have been produced using sensors and methodologies that are very consistent through space and time. And these sort of maps, they allow for comparability. I mean, you can see here that we have a map of forest change covering the whole globe. But it's very important when we use these sort of products, it's very important for us to ask ourselves, like, have these maps been validated? And if they have been validated, how? Have these maps been validated consistently across the globe, across regions? Are there any regions that have been more consistently validated? And this is usually the case. You will find that there's much more validation points in Europe, for instance, than in the rest of the world. So it's important to know how these products have been validated. But it's even more important to attribute the right drivers of change. And then again, it's the point of looking at a map that shows us some sort of trend, but that is absolutely meaningless if we are not able to truly attribute the right drivers of change. You know, what is leading to forest loss or gain elsewhere? You know, it's extremely important to answer these questions, because if we attribute the wrong drivers of change, then we will get the wrong conclusions. And if we get the wrong conclusions, any policy action derived from this assessment is completely biased, and it's actually missing the point. And this is, I think, the paramount example of this problem. It was this year when the Joint Research Center of the European Union published a report using this very same map here, the Hansen forest change map. So the JRC published this report addressing forest loss in Europe in the last, from 2016 to 2018 and from 2004 to 2015. And the idea here was to see where there's been the largest amount of forest loss and why. Now, the problem is that this report attributed most of the forest loss to clear cut and felling. And it attributed it so because it claimed that there has been an increase in the forest-related business, which is absolutely true. But the report claimed that there had been 69% of the change of the loss that we see in forests in Europe is attributed to clear cuts and felling. Now, this immediately raised some brows in the scientific community. And so some researchers went and combined these forest loss with national statistics. Actually, so that's validation data, national statistics on forest loss. And what came out is that this report had completely missed the fact that a large share of forest loss in Europe, which was due to natural causes, and that's forest fire, wind damage and storms, pests. So we have the bark beetle, huge cause of concern, and the pine processionary in Spain. So we are missing a key point in this report is that actually due to climate change, we see much more of this windstorm damage. We see much more forest fires. We see much more effect of pests in forest. And this was completely dismissed by the report. So very important to always attribute the right drivers of change, sorry. And then the one last point, I talked about validation, but as equally important as validation is uncertainty. And let's start by saying it very clear. Any map that we produce is always and necessarily an oversimplification of reality, and especially when we are looking at remote sensing. So this is something that it is as it is, and that's why there is an urgent need to address uncertainty. So this is the fact that we need to move beyond these overall accuracy models, and we need to disaggregate our uncertainty assessments by ecosystem types, by habitats, by countries, by regions. It's very important to be open about our algorithms and about our assessments. And so validation and uncertainty, actually, in a way, they force us scientists to be very open about our data, and ultimately, this leads to reproducibility, And again, an example, and I'm bringing the biomass maps from before that we computed using Sentinel. So if we look at the overall accuracy of our model, we got an R-square of 0.7, which is pretty good considering that it's a countrywide scale assessment. And so we already were patting ourselves in the back like, oh, we developed this amazing random forest model, and look at that. It's 0.7, fantastic, ready to publish. But is it right to report one single R-square, for example, for whole country, when we are assessing biomass in possibly something around 6 or 7 different grassland habitat types? So what happens if we break down that assessment? So just to show you the biomes or the habitats, sorry, that the habitats that we are looking at and the different accuracies that we got. If we look at flooded meadows, these are very homogeneous, structurally very homogeneous swards in the grassland. So of course we get a very nice R-squared of 0.8, excellent model. But if we move with the same model to coastal meadows, and coastal meadows are already a bit more patchy, a bit more heterogeneous, then we will see that our accuracy assessment is dropping a little bit. The accuracy of our model is going to 0.7. If we move to the meadows on the right side, which are albar meadows, very common in Estonia, and you can see already the structure of these meadows is much more complex. There's a very clear woody component there, so there's these shrubs in the landscape. And this, if you think that we were using a 20 meters per pixel Sentinel data, so all these shrubs are already mingling a little bit with our spectral signal, and obviously, the accuracy of our model drops down to 0.45. So that's why it's very important to disaggregate as much as possible and be very clear about the accuracy of our models when we are mapping change and when we are mapping ecosystem services using remote sensing. So just to finish this, I give you what's my recipe for mapping ecosystem services change using remote sensing, and the 4 points that we should always try to keep in mind. And first and foremost is the need of field survey data. Field survey data is going to help us train our models, but it's also going to help us validate our models so that we can actually see how far we are from reality with our remote sensing predictions. Extremely important, we need to use the right terms. We need to distinguish clearly between ecosystem processes, ecosystem functions, and ecosystem services. And then stemming out of that field survey data, we need to validate whichever model we produce. We need to be very clear about validation results, and we need to address uncertainty of the models. And yeah, with this I'm done, and then I'm happy to answer any questions that may come to your mind. And that was 30 minutes sharp.
So we have several different questions, and
all right.
So
okay, so several questions. Can you elaborate more about what CISES is? Yeah, well, I forgot the acronym for this study, but if some of you guys can help me with the acronym. The common international classification for ecosystem services could be, anyways, it's a framework to classify ecosystem services by type. And it basically, what it gives us is comparability across assessment, so that, let's say that it sets a common language. So if I talk about CISES ecosystem service 1.1.5.3, then I can go to the CISES table and see that this is biomass for energy. But there are many more different classification schemes, and this is down to your choice. But I always go with CISES because CISES has, at least in the European Union, it's connected to policy making.
So Rifa, she asked, can we count the species population of an area? Rifa, if you able to turn on the mic is better. So we're not sure what you talk about, the tree species, vegetation species, or animal species.
Can we map? So the question is, can we map species using remote sensing?
Yeah. For vegetation, yes, but I'm not sure.
I mean, that's well,
animals.
I could. Yeah, about animals, only if we are using UAVs, that's drones and thermal cameras, then of course there's absolutely amazing, and that's remote sensing as well. So, but yeah, this question could go for a whole 1 hour lecture, but yes, we can map species. It all depends on the structure of the ecosystem. But for instance, we can produce, based on Sentinel, we can produce tree species maps, and there's plenty of works you can go and search. There's plenty of works, but it all depends on your spatial resolution and on the ecosystem that you're looking at. You know, it's not the same to map species in a forest using Sentinel as it is to map species in a grassland. In a grassland, I would never be able to use satellite data, but then I could use drone data, for example, which we have. And so, yeah, it is possible, yes.
And Helena, she asked, is it possible to estimate carbon stock for the whole India without field survey? Yes, I think you can do that, but there's very high uncertainty, right? Like super high.
Yeah, we go back to the idea of validating your models. You can do it. And actually, when talking about carbon stocks, it's very tricky because with remote sensing, the only fraction of the whole carbon stock that you're going to be able to measure is the above ground biomass. The below ground biomass you could estimate, and the soil carbon storage, in some cases, it's depending on the tree cover directly. In some cases, it's not. So it's a bit more complex modeling when it comes to carbon assessments and carbon pools. Let's see, there's a lot. I like this one. How does the ecosystem services research community reach out to policy and economic actors? Yeah, in the Isla del Carmen example, this was purely a research approach, but I can tell you my experience in approaching policy actors, but I think there's people in this room that have much more knowledge than me on this. But at least my experience when we did the mapping and assessment of ecosystem services in Estonia, the best way to reach out to policy actors is to be extremely didactic about what the message that you're trying to convey, and starting from the very basics of what are ecosystem services and repeating concepts as many times as needed. Really, it doesn't matter if you have to organize 15 workshops on the same topic, if that's what's needed. So being didactic to reach out to policy actors, I think that's a key component. Nice, somebody put the CISIS website there already. Okay, so the mapping of species was referring to animals. Yes, to animals, that's the only way to do it is to use drone data, and in some cases connected to thermal cameras.
So there is another question from Lucia. She asked specifically for the grass assessment, like were you able to detect different grass species and communities through remote sensing?
Look, using satellites, we were able to detect different habitats. So we were able to distinguish a flooded meadow from a chalk grassland, for example, or from a wooded meadow. But that's how far you can go with a 20-meter or 10-meter resolution. Then we used actually again drones and UAVs to map species, but that's already at the grassland level, you know. So, but you have to think that with UAVs we get spatial resolution down to 5 centimeters per pixel, for example, which is what we used, 10 centimeters per pixel. So in that case, we are able to map different species. Yes. All right, I think we have covered.
Yes, there's still questions in your mind.
Go for it.
She asked about, so how difficult to develop an algorithm to predict change, like you did in the Glasson study, and who developed them? Mathematicians and computer scientists? What sort of training you need to be able to develop them?
Okay. Well, for example, the very detailed insight in the grassland biomass research. So in that case, we covered, I think it was 5 years with satellite data. And so we needed to code a random forest model, first of all, for year, let's say time 0. We coded a random forest model, we calculated several vegetation indexes, and then we used those 500 samples to train the model, and we got a map of biomass for year 0. And then we computed several years going back, so year -1, -2, and so on. And we applied the same model to those years. So, I mean, it's not the most straightforward assessment, but I would say it's not too difficult. It doesn't take so much time to learn just a little bit of R, snippets and code bits here and there. I'm a horrible coder. I'm awful. So what I do is I copy bits and pieces and then I paste them together and then I get tons of errors, and for a week I'm pulling my hairs out, but then it works. So you have to go through some of that process, I believe. When mapping change in terms of phenology, the story changes completely because there are loads of algorithms dedicated only to phenology, and we have, I don't know, there's a lot. There's Hans algorithms, Slavitsky-Golay algorithms. So it depends what change you want to map. You will have different approaches, you know, and in some cases you will find that there's already inbuilt algorithms that you can use, almost like plug and play sort of thing.
Yes, like many of these algorithms have been developed long times ago, and we start to have the computer process ability to actually apply those in handling remote sensing data.
Yes, absolutely. can you provide some references using MATLAB in ecosystem modeling? Well, I'm not a MATLAB person, but I know that if you attempt to use MATLAB for phenology assessments, you can look for this. I think this is built. I will just write it there. For instance, for phenology assessments, I know that you can use that particular algorithm in MATLAB. Sometimes I have the feeling somebody says, or sometimes I have the feeling I'm the only one who finds it challenging. No, you're not alone, Lucia. You're definitely not alone. I think
so
we all.
Yeah, it's hard. I also have a question because I also want to ask you about the field. We only emphasize on the field data, but now we have so many remote sensing data. Do you think one point, like some point in time, we might be able to only use remote sensing data without the field survey?
No. The interpretability of remote sensing will always be linked to what we measure on the ground. You know, there's only how much further we can get with remote sensing. Actually, we are already hitting the limit with the spatial resolution. You know, you were showing this. You were showing these 3 meters per pixel, which is absolutely amazing, but we're not going to get much better than that. And we're not going to get much better. I mean, we may get more radiometric or more spectral solid products, but we will, I'm sure that we will always need training and validation for our models. Yes.
So is there any other questions? I think we addressed all of them.
Nice.
Class, do you want to say anything?
Well, for me, this is always a little new. Coming from the social scientists, I always have I've done a couple of introductory courses on mapping and modeling, and have kind of broken my motivation at the level of trying to copy some code and it only giving out errors. But it's definitely always interesting to hear about what you can do with those kinds of technologies. And I think it's important to at least try to make an effort to understand what you guys are talking about. I guess I'm still at that stage, so this was really again introductory to me, but it was great how you guys summed up some of the technical aspects as well, and some of the main questions. So this was really, somebody said, enlightening, but really a good overview, I think. Thank you so much for organizing this also and for being available on a Saturday.
Yeah, thank you guys for coming in the weekends. So if we don't have any other question, then I think the time is almost finished. The time is there as well. Thank you. So again, thank you so much for coming today. I know we were organizing it in the weekend, and but you guys all show up, and that was very great. And I had a very good time with you guys. So this session is recorded and we'll publish it on YouTube channel, I believe, right? And so we will send you guys the link when it's possible. And thank you, Miguel, for coming today. It was great having time with you and work with you that's several weeks. And thank you guys for coming today. I think we can stop the session now.